Hello everyone, in this video we will discuss about the types of fluids and we will also discuss about this graph. As you can see, the shear stress tau versus the velocity gradient du dy graph. We will discuss it in a very brief manner, and first let's get started with the types of fluids. You can see ideal fluid, real fluid, Newtonian fluid and non-Newtonian fluid, and ideal plastic fluid. So ideal fluid is a fluid which is incompressible and having no viscosity. So it is not possible. So it is an imaginary fluid. But in case of a real fluid, it will possess viscosity and it is known as real fluid. Okay. So Newtonian fluid is a fluid which will follow the Newton's law of viscosity. So what do you know from Newton's law of viscosity? We saw that tau is proportional to du dy. So we brought a constant which is tau is equal to mu du dy. So if this equation is being followed by any fluid, we will say that this is a Newtonian fluid. And if this is not being followed, we will say that this is a non-Newtonian fluid. And what is an ideal plastic fluid? See the line of ideal plastic fluid. So in which shear stress is more than the yield value, and the shear stress is proportional to the rate of the shear strain. So velocity gradient also. So it is known as the ideal plastic fluid. So we'll discuss all of the above each by each. Okay. So let's get started. So first, see, in this case, this is the Newtonian fluid. Okay. So the pink line that you can see, we have already marked it here. This is the graph for the Newtonian fluid. So in the x-axis, we can see du dy, which is the velocity gradient or the shearing strain also. So you can also put d theta dt here, right? We know that because du dy is equal to d theta dt. Okay. Now, to the y-axis, we can see we have got the shearing stress. So from the Newton's law of viscosity, we know that tau is equal to mu du dy. So from here, if you place y here, because it's in the y-axis, the tau or the shearing stress in the y-axis, and this is in the x-axis, and thus if I assume that this is my m, which is the slope, right? So y is equal to mx. This is the equation for a straight line where m is the slope, right? So it will look something like this. So this is my equation in which this is my slope, this is x, this is y. So we can see that this is my slope. And what is the meaning of slope? Slope is the change in the y direction divided by change in x direction. So if you want to figure out any slope, we will use this formula, right? So now as we move forward, we can see that in this line, in this pink line, which is following a straight line equation and having a slope m, and this is having a slope m. This is the m slope, right? Okay. So in this m slope, what is the meaning of slope in this case? Because we have seen that slope is equal to the change in the y direction divided by change in the x direction. So we can say that the slope is equal to change in the y direction. What is being changed? What is the variable parameter in the y direction? That is your stress. And what is the varying parameter in your x direction? That is du dy. So you can see m is equal to tau du dy. So you can write nu in place of this, right? See, from here you can find that nu or your viscosity is equal to tau divided by du dy. So from this equation you can say that m is equal to mu, or your slope is indicating you towards the value of the viscosity. From here you can figure it out. So your slope is indicating you towards the value of your viscosity. So here you can see that this value and this value is equal. That means here your viscosity is remaining constant. So that means as your viscosity is constant, you can say that tau is proportional to du dy, right? That means the more the shearing stress, the more the rate of shearing strain. So in this case, this is your Newtonian fluid. So what can be an example of your Newtonian fluid, right? A great example of Newtonian fluid is your water and air. See, this is your Newtonian fluid. That means the more is your shearing stress, the more will be the du dy, or the more is your shearing stress, the more is your d theta dt. Now let's discuss about shear thinning fluids. So what do you even mean by this shear thinning? See, here as we increase the rate of shearing strain, so we see that we get a curve like this. And see, look at number 1 curve. We get a curve like this, and this is a concave downwards curve. This is a concave downward curve, and we know that if the curve is downward, the slope is decreasing. So as the slope is decreasing, I have already told you that slope is equal to viscosity in this case. So as the slope is decreasing, you say that the viscosity is also decreasing. That means the more you apply the shearing stress, the more you lose your viscosity. That means less viscous the fluid gets. So this is your shear thinning. So example for this is latex paint or ketchup. Okay, so the more stress you apply on it, the less viscous it gets, because its gradient, its slope is decreasing, as it is a concave downward curve. It's a downward curve. Okay, so now take a look at this shear thinning curve. What is it actually? See, it is actually a concave upward curve. So an upward curve will have an increase in slope, and because the slope is increasing, we can say that our slope is equal to viscosity. So as the slope is increasing, our viscosity will also increase. See, as the slope is increasing, our viscosity is also going to increase. And what is the example for this is cornstarch. Okay, so we have got to know about shear thinning, shear thickening, and Newtonian. So except Newtonian, all the other curves that you can see here are non-Newtonian fluid flows curves. Okay. So next we move to Bingham plastic. So as you can see from this curve, that this is not starting from the origin. So it's not starting from the origin. It means that you need a threshold force for this Bingham plastic to start flowing it, right? So what is an example for this? A toothpaste. So imagine you have a toothpaste in your washroom. You may have a toothpaste. Just bring it, and if you put it upside down, if you keep it like this, this is your toothpaste. Okay, so this is your toothpaste, and if you are keeping it like this, it will not start flowing. But if you squeeze it, it is going to start flowing. It is going to have a flow. So that means it needs a threshold value, a amount of threshold value to start its flow. So that's why you call it Bingham plastic, and this is also known as ideal plastic fluids. See, this is also known as ideal plastic fluids. Okay, so we have already discussed about all of the different fluids and the examples of them. And so we had a shear thickening fluid like a cornstarch and water mixture, which is also known as oblique. So here the curve will bend upward, as you have seen in the picture. The curve is bending upward. The curve is bending upward. So it means as the curve is bending upward, it means that as we are moving along the x-axis, which means the increase in the shear rate, the slope is increasing. So as the slope is increasing, I told you, as the slope is increasing, our dynamic viscosity or viscosity will also increase. That means viscosity is increasing. So we can say that the more force you apply, the more tangential stress. It means the more force you are applying, the more thicker or the more viscous that fluid gets. Okay, so this is why if you punch oblique, it feels like a solid, but if you let it slip, it flows like a liquid. Thank you so much for watching this video. I see you in the next time.